off, we were talking about parameter estimation. We're in the section on parametric models, just kind of the general framework, which will soon apply to a few simple parametric models. We were talking about parameter estimation, and the big new idea there was this idea of marginalization, doing integration over parameter space. So statistics in general is essentially, mathematically, it's all about integrals and sums, right? Averages, probabilities by integrating under curves, things like that. So frequentist statistics is all about integrals and sums in sample space. Mathematically and computationally, Bayesian statistics is all about integrals and sums in parameter space. And that's what I'm trying to kind of harp on in these first lectures. And marginalization is just an example of, and a recurring example of the way that integration, summing over parameter or hypothesis space appears in Bayesian calculations. This is also the way to think about, in terms of coding, being a programmer. This is the way a Bayesian code differs from a frequentist code. All statistical codes in some level, implicitly or explicitly, are doing some kind of integration. And what the new kind of computational technology you have to learn about to write a Bayesian code is, how do I do integrals over parameter space instead of over sample space? Sample space integrals you usually do by simulating data. It's pretty straightforward. How do you do integrals over these parameter spaces that might be correlated in complicated ways? So that's what I'll briefly talk about at the end of my lectures tomorrow, and Brandon and others will tell you more about the rest of the 2 weeks. So we talked about marginalization in the context of single model inference, but now let's talk about model comparison, where you'll see that it plays an important role. So in model comparison, kind of our background assumption is that we're specifying a set of models, and we're going to assume that one of them is an accurate description of the data. We'll leave for model checking to assess whether that grand hypothesis itself is reasonable. So one of these, this is the statement that, either model M1 or model M2 and so on is a good description of the data. This set can be finite, or it can be countably infinite even. Polynomial expansion in all orders up to infinity. There are situations where you can actually formulate these things in a correct Bayesian way. And now the hypotheses of interest now are the choice of a particular model. M3. Meaning hypothesis. My hypothesis is that M3 is the right description. So another way to think of it is the hypothesis space is just the space of integers, I. Is I equal to 1, 2, 3, or you might pick a null model, 0. Is I equal to 0? So we have a hypothesis space, we have premises, and we're going to get some observed data. So we just calculate Bayes'. We just use this Bayes' theorem to get a posterior distribution over the hypothesis space, the choice of models. So it's going to be a prior for the model as a whole, the probability for the data given the model, not saying anything about its parameters at the moment, and then a thing in the bottom that's a normalization constant again. So this, symbolically, there's nothing new here. It's just Bayes' theorem again. Posterior is proportional to prior times likelihood. But now this prior is a prior, not a prior density over a parameter space of one model, but a prior probability, a probability mass function in the language of probability theory, a prior probability over integers. Maybe there's just two. And then a likelihood for the model as a whole without reference to a particular value of its parameters. So that's something that we haven't talked about before. This is just a probability over integers, but what the heck is this? A likelihood for a model, not saying anything about its parameters. Well, what is this? So this is P of D given M sub I, and the statement that either M1 or M2 or M3 is true. Well, if I think of I equals 2, for example, P of D given M2 and the statement that either M1, M2, M3, or so on is true is just the probability for P of D given M2. So I've written down here. So the likelihood for model I is the probability for the data given model I. But this you have seen before. This would be the denominator of Bayes' theorem when I'm doing parameter estimation for model I. So remember the denominator in Bayes' theorem back, in parameter estimation? That was the uninteresting normalization constant. Now that thing, when I'm doing model comparison, comes into the numerator, and instead of being an uninteresting normalization constant, it's now the thing that calls the shots. So I wrote it out for you again. Remember, you do this by extending the conversation or using the law of total probability. You introduce theta, factor, and then integrate. So P of theta, P of D given theta, and integrate. So this thing, remember, it's the prior predictive probability for the data given a particular model, or it's the likelihood for that model, which we're showing here is equal to the average likelihood for its parameters, the average of the likelihood function. So this is a conceptually new thing that Bayesian inference gives you. Something like this does not arise in any natural way in frequency statistics. The idea that the likelihood of a model with uncertain parameters is the average of its likelihood function, weighted by the prior. There's varied terminology for this. I've already mentioned a little bit about it already. In terms of what it means as a function of the data, it's the prior predictive for the data. But we're interested in what it means as a function of the hypotheses. So kind of most straightforwardly, it's an average likelihood. Some people have called it the global likelihood. The most common term and the recommended term is the marginal likelihood. A horrible term that's been in use in astronomy and physics is to call this the evidence. Please don't use that if you can at all. Avoid it. The evidence is the data. That's the way the term evidence is already used in the Bayesian literature and in the philosophy literature. If you want to talk about this, there is some use of the term weight of the evidence. You're bound to call it evidence because a lot of cosmologists do, but I just want you to know that that's not the standard term in any other area but astronomy and physics. Another reason why I loathe this term, evidence, is because there's only two types of quantities in Bayesian inference. There's probabilities for things on the left of the bar, and there are likelihoods for things on the right of the bar. And to introduce another terminology for this thing is to suggest that there's some conceptually different third ingredient. When really, this is just, it's the likelihood in a different space, the space of competing models versus the space of different model parameters. So conceptual cleanliness means just think of things in terms of probabilities and likelihoods. If you call it evidence in your paper, please also use the term marginal likelihood so it shows up in searches. This is the thing that everybody else in every other field will search for. So just make sure, if your particular area of astronomy likes that horrible term evidence, just make sure you have a footnote that says this is also called the marginal likelihood, just so it'll show up in searches. All right. Now, since we're in a discrete space, and a space labeled by integers, we can do some things that are not so easy to talk about in a continuous space. You can talk about ratios of probabilities for competing hypotheses. So a ratio of probabilities for two propositions using the same premises is called the odds favoring one over the other. So here the premises are the data and the space of models. So the odds favoring model I over model J are just a ratio of their posterior probabilities. Now, each one of these can be written as a prior probability, a model likelihood, and then a normalization constant. But the normalization constants are the same, so they'll cancel. So the odds can be written as the product of these two ratios that each have a name. I didn't write down the name of the first one. This is called the prior odds for hopefully obvious reasons. So it's the ratio of the probabilities just based on the prior information. And this thing here is called the Bayes factor. And that's the term that tell you how the data change the odds. And so that's kind of a key piece. That's the data-dependent piece of model comparison. It's basically just a likelihood ratio. If you've done likelihood ratios or calculated delta chi-squareds between models. That's a logarithm of a likelihood ratio proportional to it. Then you've done things like this. The difference here is that in the space of competing parametric models, you're taking the ratio of average likelihoods, average likelihood function. Whereas the thing that typically arises in frequentist statistics would be the ratio of maximum likelihood functions. And that difference between whether you look at the average of the likelihood, which takes into account parameter uncertainty, or the maximum, which just focuses on the one best fit value, that leads to qualitative differences between Bayesian and frequentist comparison of models. So one way that's phrased is that the Bayesian approach introduces or kind of implements a kind of automatic and objective, in some sense, Occam's razor. So you may have heard of Occam's razor, this idea that you should prefer simpler things unless there's strong evidence for more complicated things. It's named after William of Ockham. So he came up with this phrase, and let me see if I can remember it. Entities should not be multiplied without necessity, something like that. Does anybody remember the exact phrase? Anyway, he was one of the first people from a philosophical point of view to write explicitly about the idea that there should be a preference for simplicity. And what I want to show you on these two slides is just to convey qualitatively and semi-quantitatively the sense in which Bayes factors or the marginal likelihood computation implements this kind of preference for simplicity. So we're going to look at it at two different ways on these two slides. This first one is kind of more qualitative. So the average the likelihood for a model, the marginal likelihood, is just the likelihood function averaged over with respect to the prior. But its meaning is that it's the prior predictive probability given a particular model. Now, one of the things we know so I want you to imagine for both of these slides we're in the setting of nested models. These are models where there's a simple model with some set of parameters, and then there's a competing model that has those same parameters and one or more additional ones. So that the simpler one is a special case of the more complex one. Is that clear? So, like, is there a source in this image or not? There's a simple model, which is that there's only background, and then there's another model that adds the magnitude and the location of the source, 3 new parameters. So those are nested models. So one thing I think you probably all know is that once I add new parameters, I can always fit things at least as well as the simpler model, but the fact that I have new parameters means that almost always I can fit better. Whatever the data set is, whether it came from the simpler model or not, I can always fit it better just by fitting noise with the extra parameters. So now recall that this thing is the prior predictive probability, the ability of the model to predict data, not taking into account the data themselves, right? So for a simple model, the description I just gave you, the relative predictive power of nested models, means that a simple model can only give high probability to a subset of the data that can be explained by a more complex model. So a simple model has to have, in the space of all possible observations, it has to have a more peaked distribution of its predictive distribution than a complex model. A complex model, since it can be tuned to more data, since it has to be normalized, since its predictive distribution has to be normalized, if it can fit this data better than the simpler one, then it must be able to predict this data with less probability, because it has the same amount of total probability, 1, but now spread out over a wider variety of data that it's capable of tuning to. So that's just a qualitative argument that says for a complicated model, this thing has to be more spread out than this. So there has to be places in the data space where the prior predictive probability of the simpler model can be bigger than for the complicated model, even though once I fix the parameters, the complicated model can predict those data with even higher probability. this thing is averaging over the parameters, and the qualitative hand-wavy, I admit, argument that I just gave you is to say that those models, their predictive distributions must look something like this. But now let's say something a little more quantitative. Let's actually look at the form of this this integral, this marginal likelihood integral. Now, we've done this same kind of approximation before. When I talked about the marginal likelihood function and the profile likelihood, we talked about the likelihood being peaked with respect to the prior and pulling factors out of integrals. Let's go through that same argument again here. So I imagine there's a likelihood function. The data are informative here. It has some width, delta theta. It peaks at some theta hat, which I didn't label here, but should have. And then there's a prior that's diffuse. It's over some prior search range for the parameter big delta theta. So let's look at this integral just kind of semi-quantitatively. So the prior is roughly constant over this region where most of the likelihood area is. So let's pull it out of the integral, evaluating it at the peak. So p of theta hat, I pull out of the integral. And then let's do the integral of the likelihood, but approximate it by its peak times its width. So likelihood of theta hat times the width, delta theta. So I'm going to rewrite this as the maximum likelihood times the width of the likelihood function, and then I'll make a further approximation. The value of the prior at some point, roughly speaking, just by a scale argument, it has to be 1 over the width of the prior, the size of the search range, at least in some rough sense. So what I've shown here is that, roughly speaking, the marginal likelihood is the maximum likelihood times this factor that has to be less than or equal to 1. It's a ratio of the posterior width to the prior width. It's a parameter space volume ratio. It's like, in some sense, since it's much less than 1, it's like it's the fraction of parameter space that's being used by the model. Fraction that actually gives high probability to the data. It has a name. It's sometimes called the Ockham factor because it's a penalty. It can be viewed as a kind of penalty that takes the maximum likelihood, the highest probability for the data, but penalizes it for the fact that, well, yeah, that's the highest probability if you knew the parameter values, were the best fit values, but in fact the parameter values are uncertain. Once you take into account the uncertainty, there's this penalty factor that's basically the wasted volume of parameter space. So models that have more parameters can make this bigger. They'll never be smaller, and the extra parameters potentially will make this bigger. But the extra parameters introduce extra factors here that will be less than 1 that will penalize models with new parameters. So this implements this kind of preference for simplicity because a model whose best fit is better will not be favored unless it's enough better to make up for the waste in parameter space by the new offered by the new parameters. This has actually been latched onto by philosophers of science as a very nice kind of quantitative description of the idea that models shouldn't require fine-tuning. You hear this talked about a lot in regard to, say, lambda, the vacuum energy. Why is it so near 0? Well, the idea there is a priori there's no the prior probability for what lambda should be is actually over a very large range, which scales much bigger than where it currently is. The data offer you evidence that's concentrated to a small value compared to that range, and this nicely encodes that kind of fine-tuning argument. And that's a kind of uniquely Bayesian thing. I mentioned Bayesian model averaging earlier, and we just don't have time to get into it. But some of the math is here if you want to learn about it. So let me wrap up this section of this lecture, and then we'll finally get to parametric models, to real parametric models with formulas. But just to tie up this section, I want to emphasize again, a main theme is the role of parameter space volume. So Bayesian probabilities, kind of the new thing conceptually about Bayesian inference is you're allowed to talk about probabilities in parameter space. The laws of probability theory then direct you to do all kinds of sums and integrals of probabilities over parameter space. And it's those parameter space integrals that buy you a lot of the power of Bayesian methods. Things like credible regions require integration over parameter space. Those resemble confidence regions but are different in general because it's a different kind of integration. Marginalization is essentially Bayesian idea that ends up weighting this frequentist ingredient, the profile likelihood, by a volume factor for the nuisance parameters. And then in model comparison, model likelihoods have these Ockham factors that come from these volume integrals, ratios of kind of volumes in parameter space. A lot of the virtues of Bayesian methods can be tied to these integrals, these kind of parameter space volume factors that appear. Now let me say one final thing about priors. You've probably already heard about priors even if you're pretty new to Bayesian inference, and kind of an obvious thing about priors is that they encode prior information. But I want to point out that there's actually two quite different roles for priors in Bayesian inference. The first one is the obvious one. They're a handle in which you can bring in prior information if you had it. They're also, frankly, a nuisance when you don't have prior information and you have to assign them. It's not so big of a deal in some parametric problems, but it becomes a very big deal in non-parametric Bayesian inference, which we're not talking about here. So they're sometimes a nuisance, sometimes important for this. But there's a second role that they play. They convert the likelihood from an intensity to a measure, and they enable all of this accounting for parameter space size. So what do I mean by this? Convert likelihood from an intensity to measure. Well, I'm making an analogy to the concept of intensive and extensive quantities in statistical mechanics or thermodynamics. You probably remember all about that. There are some things that are intensive and then some things that are extensive that add up as you increase volume or bring in more material. So for example, temperature is an intensive quantity in thermodynamics. There's a temperature field in this room for the temperature of the gas in this room. At any one point, it's meaningful to talk about the temperature at that point, but it's not meaningful to add up the temperature in the room, to integrate temperature over volume and say, well, the total temperature in the room is the integral of temperature. That doesn't make sense. We say that in physics speak by saying temperature is an intensive quantity. It's not meaningful to integrate it. But temperature, we know, has something to do with warmth and heat. And so there is an intensive quantity. There's a total amount of heat in the room. There's a bit of heat in this volume, and I get the heat in the room by adding up all the volumes, and that's related to temperature. Heat is the integral of the heat capacity times the density, multiplying the temperature. So there's these factors that convert this intensive quantity to heat, which is an extensive quantity. In mathematics terms, heat is a measurable quantity. A measure is something that adds up in space, whatever space you're looking at. So in a quite close analogy, in probability theory, likelihoods are an intensity, an intensive type of quantity. They're not a probability as a function of theta, so you're not allowed to add them up over theta, sum or integrate them over theta. Bayes' theorem, through the prior plays the same role as density and heat capacity in thermodynamics. It converts the intensity to a measure, which gives you something that does add up over parameter space instead of physical space here. So another way to put it, this analogy, is that maximum likelihood, kind of a cornerstone of a lot of frequentist statistics, focuses on the highest temperature parameters, whereas Bayesian inference focuses on the parameter regions with the most heat. It's interested in volumes in the parameter space, not points. A high temperature region in thermodynamics can contain little heat even though it has high temperature, if its heat capacity is low or its volume or density is low. Similarly, a high likelihood region may contain little probability if its prior is low or if the volume associated with it is small. Like in model comparison with nested models, a more complicated model might have a big peak in its likelihood function, but if it's very narrow compared with your search range, your prior range for that parameter, then in fact its total probability is small and it's not favored by the data. So that's so keep that in mind about priors, that they're not just this handle to bring in new information or sometimes a nuisance to have to worry about ignorance, but they're also this thing that lets us do the volume integrals that bring us all the cool things that Bayesian inference gives us. So this is the end of this first half, and we're going to spend the last 25 minutes or so of this lecture doing the first of our actual parametric models. But just the recap of the key ideas. Probability is looked at as a generalization of logic from the Bayesian point of view. It measures the relative strengths of arguments to different hypotheses. It uses all of probability theory, not just Bayes' theorem. So it's called Bayesian inference after Bayes' theorem, but I hope you got the point already that it's not just about or even primarily about Bayes' theorem. In terms of your codes, it's primarily about the law of total probability, actually. And then the two most non-trivial important theorems are Bayes' theorem, posterior proportional to prior times likelihood. It says that the data change the support of a hypothesis proportional to their ability to predict the hypothesis. Completely reasonable idea. And then there's the law of total probability. Just qualitatively, it just says that the probability of a compound hypothesis, like the probability for a model that's comprised of many different possible values of parameters, the probability of a compound hypothesis is the sum of the probabilities of its constituent hypotheses. The support for a compound hypothesis must account for all the different ways it could be true. You know, in parameter marginalization, the posterior marginal for a source parameter, a signal parameter, has to take into account all the different ways the background parameter is or is not supported by the data, estimated by the data. That kind of argument. So now I'm going to switch slides to my next set. Oh no. When we change resolutions, all my folders vanished. Let's see. Okay. Now I want to take all that somewhat abstract stuff and apply it just to kind of a few cornerstone, simple models, just so you could see how it works out with formulas instead of just abstract symbols, actual, formulas for distributions. There's kind of a holy trinity of models, of probability distributions that appear over and over in a lot of physics and astronomy. The binomial, it's related to the Bernoulli distribution, the Gaussian distribution and the Poisson distribution. So we'll go through some examples with those. We'll see how far I get in the next 25 minutes or so, and then we'll pick up the rest tomorrow morning. I'll probably have to cut some of the other stuff I wanted to talk about because I'm going a little more slowly than I anticipated, but let's get started with just these key examples. So we'll start with the binomial distribution. It's really about the relationship between probabilities of an outcome and how often that outcome arises in a set of trials. There's lots more that I would like to tell you that I think is important for users of Bayesian inference to know, even with these simple models, much more than we can cover in just an hour or two. So there's a supplement document that I'm putting online where I'm going to cover some other topics related to these three distributions. So binary classification, the negative binomial distribution and stopping rules, something called the likelihood principle, which we'll just very briefly see an example of here, other relationships between probability, frequency, and other things that will come up along the way. So those will be in a document online. If you want to look at that this week, that might be a good idea if any of those topics look interesting to you, because then you can talk with me if you want to get cleared up. I tried to make them readable standalone, but we'll see. All right, so let's get started with binary outcomes, binomial distribution. So the idea is there are two different outcomes, like success, failure, heads, tails, star, galaxy classifier in an image classifier. And there's many trials, many sources on your frame that you want to classify as a star or galaxy, many flips of a coin. We're going to say that the probability for one outcome, the success outcome, is alpha, meant to signify proportionality. And then for failure, it's 1 minus alpha. So there's two outcomes, but really only one parameter, alpha. The hypotheses would be statements about alpha, the probability for success on the trial we saw or on the next trial by assumption. So we're going to look for, we're going to do parameter estimation. We're going to look for the posterior density for alpha given some data. And we're going to look at two different types of data in this lecture, and the supplement talks about another type or two. So imagine for the data that, thinking of flipping coins, or we had the sequence of results from n observed trials. So failure, failure, success, 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 failure, 3 successes. So we're actually given that sequence. We can think of it as zeros and ones, 0, 0, 1, 1, 1. So it's a binary sequence, star, star, galaxy, 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 star, star. In this case, I'm going to use some symbols, little n for the number of successes, big N for the total number of cases. The likelihood, the probability for this sequence of outcomes, well, it's just a product of all their independent probabilities. So the probability of failure given alpha would be 1 minus alpha. Probability for success would give you an alpha. There'll be n alphas and big N minus little n 1 minus alpha, so that's the probability. The name for this thing in statistics is called the Bernoulli process, kind of a fancy sounding name. So the Bernoulli distribution just refers to the probability for one of these outcomes. It's, alpha if it's success, 1 minus alpha if it's a failure. That's a probability distribution over a discrete space with two elements in it. A process, a stochastic process, is an indexed set of probability distributions all over the same space. So in this case, the index is just the label of the trial, the first trial, second trial, third trial. So that's why this has the fancy name Bernoulli process. So there's a Bernoulli distribution at each trial. The sequence of trials makes this a stochastic process. So you've already, I'm sure, have seen probabilities like this. You probably didn't know you were doing stochastic processes. So, yes? So this is a probability for this particular sequence. So it already is normalized over all possible sequences. If there's n, there's 2 to the n possible sequences, and the sum of all these possible probabilities just gives you, if you sum these, there are just 2 to the n of them, only 1. You're thinking of the binomial distribution, which we'll get to in a minute. Okay. So this is a Bernoulli process. So this is the likelihood function for alpha. So now we need a prior. So we need to assign some prior, and we're going to imagine this is our first data set we're looking at. So we need to assign some prior that expresses some notion of not favoring any other value over another a priori, a so-called uninformative or least informative prior. And there's a bit of an art to try to assigning these, and increasingly a bit of science, much of it due to Jose. So let me give you some arguments for this, and Jose has a more formal approach, which I'll allude to later, called reference priors, that maybe he'll talk about, or he'll tell you about reference priors. A nice kind of objective mathematical theory for how to do this, especially for more complicated problems. It's useful. But so here's an intuition. Don't prefer any interval of alpha over any other one of the same size. That suggests just taking the prior to be constant. Since alpha can be over the range 0 to 1, that means that it's 1 if it's normalized. This is actually the first argument for a prior, due to Thomas Bayes in the famous paper that started all this. He suggested that ignorance here should mean that before doing the n trials, we have no preference for how many will be successes. So there could be 0 successes, 1, 2, 3, up to n. So that means there's n plus 1, the 0 case, possible numbers of successes. And Bayes said that my idea of what ignorance should mean is that I want the probability of n successes to be this. And that is an integral, that corresponds to an integral equation for this density, which he solved impressively in his paper, and showed that the solution of that is a constant prior. That's just to say that there's more than one argument, very different qualitatively, but that all lead to this prior. The reference prior is not the flat prior in this case. So let's just adopt this as a convention for now. So that's the top of Bayes' theorem. Yes, Brandon. Yes, and just to harp on that, it's a very good point, because the prior appears here. Well, it'll appear in Bayes' theorem. It multiplies the likelihood once, but the likelihood in this case, the Bernoulli process, appears n times, n factors. So small changes in the likelihood can shift the posterior way more than small changes in the prior. So, so Brendan's point is actually very, very much worth dwelling on. That largely because of the history of history, we don't tend not to argue much about likelihood functions. There are certain problems where we kind of automatically go to certain likelihood functions or not, and then we might agonize over agonize is a good word, agonize over the prior, when really small changes to the likelihood would probably more profoundly change our results than any reasonable change to the prior. Excellent point. All right, so we have a constant prior, we have a Bernoulli process likelihood, we need the denominator. So this is the likelihood, the prior was 1, we need to do this integral. This integral, you can look it up in a book, or find it in Mathematica or on Wikipedia. It has a name. It's called the beta integral. It can be written in terms of factorials. There it is. You could do it by recursion, starting with just a simple case and doing integration by parts if you needed to. But it's just a number. It doesn't depend on alpha. You've integrated over alpha. Here it is in terms of factorials. In general, this is the definition of the beta integral. It's something to a power that needn't be an integer, 1 minus that thing to a power that needn't be a different integer, and then integrate it. And so in general, you write it in terms of gamma functions. That's why there's the 1s here, because the relationship between gammas and factorials differs by 1. It's just the name of a function. Okay. So the posterior now looks like this. The prior was 1, the likelihood was this thing, and we've divided by the prior predictive, which is, so now the n plus 1 factorial appears on the top. There it is. We look at this now as a continuous probability density function over alpha. it might look familiar to you. It might look a little like a binomial distribution, which would be a distribution for little n, but it isn't. It's a distribution over alpha. A binomial distribution would just have an n factorial here, which would normalize it summing over n. But here it's something normalized over alpha, so there's a little different constant out front. And then here are some summaries. The mode is at the frequency, little n over big N, 2/3 for the sample I showed you with 8 successes in 12 trials. The posterior mean is shifted, in this case, to the left a little bit. It's a slightly skewed distribution in general. There's a formula, a messy formula for the standard deviation, but if you look at it when the counts are large, you can convince yourself it's basically a 1 over root n type uncertainty. Now, one thing rather important to note here is that the data were 12 binary digits, 10001, that appears in the posterior only in the form of this integer n, little n. Big N was just given at the beginning. That little n, that's a function of the data that tells you everything you need to know about that data set for the inference. When you have that kind of compression of information in the data into some low-dimensional number or set of numbers, that's called a sufficient statistic. There's a more formal definition that we won't get into it, but I just want to convey that idea to you. So here's just a plot of that posterior density. That curve is the full Bayesian answer to the parameter estimation problem, but then here are just some summaries. There's the mode, there's the mean, and a standard deviation each way. Here's the 68% highest posterior density region, which you should not call the 1 sigma region because this is not a Gaussian distribution, so that's not a 1 standard deviation region. Here's the 95% region. You get these by using something called, you can just integrate numerically under the curve, or it turns out you can use the incomplete beta integral to get them analytical or semi-analytical. So that posterior is a beta distribution, and this is the general formula for that. So there's a bunch of distributions you should have in your repertoire for doing Bayesian inference. Of course, there are these sampling distributions you already know, binomial and Gaussian and Poisson, but you need to know some other ones so that will kind of operate in the posterior parameter space. So the first one you're learning about here is the beta distribution, and this is just its general form. When those things aren't integers, when those exponents that appear aren't integers, these are the formulas. You can look it up on Wikipedia or any other good reputable source. There's simple formulas for the mode and the mean and the variance. The traditional parameters are in terms of the powers, but you could also just reparameterize it in terms of the mean and the variance, or between the mode and the variance. There's all different ways you could parameterize it. In the cumulative distribution, partial integrals over part of the range of alpha are the incomplete beta function. This was a model comparison calculation, but in the interest of time, I'm going to skip that. All right, so binary outcomes. Now let's imagine the same problem, but with a slightly different choice of data. So suppose the data I hand you, I do my 12 flips, or I look at 12 sources classified as galaxies and stars. And I tell you only at the end the number of successes, the number of heads, or the number of galaxies, rather than the actual sequence. What's my posterior if I tell you only this partial summary of the actual sequence of outcomes? All right, so how can we get the likelihood function? What we need is the probability for n given alpha. Well, I don't see how to do that, obviously, just directly, but let's use the law of total probability. So imagine we knew the sequence. Let script S here be the actual specification of the sequence, a 12 binary digit number. So let's insert it on the left and then sum over it in factor. So we'll insert an S, so we'll have a probability of S given alpha and then a probability of n given S. All right, so what's the probability for, and we're going to sum this over all possible sequences. So What's the probability for a sequence given alpha? Well, we know that from Bernoulli process. Now, what's this thing here? What's the probability for seeing n outcomes if I know the sequence? Well, regardless of the probability, if I know the sequence, the probability of getting little n successes is 1 if the sequence had that many successes, and it's 0 otherwise. So these double brackets are one notation for the indicator. This is a quantity that's equal to 1 when the statement inside it is true and 0 otherwise. It's sometimes called the Iverson bracket or the characteristic function. So that's just symbolism for this. This probability is 1 if the number of successes in the sequence is n and 0 otherwise. So let's do this sum. For the fixed number of n, all these things are the same, so I'll pull that out of the sum, and I just get basically the sum over sequences of 1s for every sequence that had n successes in it. So this is telling me just count the number of sequences that have little n successes in them. And you probably have all learned how to do that. That's the number of sequences with n heads in them out of n total possibilities is just the binomial coefficient. So this is just, I just wanted to give you yet another example of the law of total probability. This is how you could derive the binomial distribution using the law of total probability. So our likelihood function is the binomial distribution for the number of successes given the total number of trials in the probability. So the posterior is prior, which will again be 1 times the likelihood binomial divided by the prior predictive. The prior predictive is the integral of the top over alpha. We have that same beta integral, but now it's multiplying this thing here. Remember, it looks just like this, but it had an n, the inverse of this, but it had an n plus 1. So when I multiply that beta integral times this binomial coefficient, I get a 1 over n plus 1. When I plug that in here, you get this final result, which should look familiar. The posterior distribution, given the number of successes and not the whole sequence, is exactly the same as before. It's the same result as when the data specified the actual sequence. This is an example of something called the likelihood principle. In the Bernoulli problem, the likelihood function was just alpha, 1 minus alpha to the appropriate powers. In this binomial case, it was that same function of alpha times a different function of the data. So looked at as a function of the parameters, it had the same behavior. It only differed in a data-dependent part. So the likelihood principle is, from the Bayesian point of view, it's just the recognition that all that matters about the likelihood function is its dependence on the parameters. Problems that have different likelihood function, different actual likelihoods, different sampling distributions, but that are proportional with respect to the parameter dependence, will give the same final inferences. That's the likelihood principle. I want to introduce one other bit of lingo here about priors. We can imagine generalizing from the flat prior to a prior that is itself a beta distribution. Remember, a beta distribution is just alpha to a power, 1 minus alpha to a different power. So imagine I were to use such a prior. So here's that prior, alpha to the power, 1 minus alpha to a different power. And now I introduce the likelihood function, which is proportional to alpha to the n, 1 minus alpha to the big N minus little n. The final posterior distribution you can see here just by multiplying the alphas and 1 minus alphas is itself just a different beta distribution. So a beta prior and a binomial likelihood gives you a beta posterior. That pattern where a prior in a certain family becomes a posterior in that same family with a particular likelihood, that's called conjugacy. You say that that prior is conjugate to that likelihood function. So I just wanted you to know of that terminology. In particular, the flat prior is an example of this. If I were to take A and B equal to 1, that is the flat prior. The reference prior is slightly different. Jose will tell you about it. I think it's a half, right? A and B are a half. So the reference prior. So just a bit of terminology. Conjugate priors are important for building models that have kind of analytic simplicity. Even if they're not the final model you want to look at, sometimes they're helpful just for you to be able to do some parts of the math analytically and get some insight into what's going on from the analytic calculation. It makes it easy to chain inferences. Remember, the posterior is a beta. So now if I imagine taking more data, more sequences, I can use that posterior as the prior for the new data. This would be the posterior, and this would be the prior, the likelihood function for the new data set. And when things are conjugate, I can just naturally chain my calculations very easily. All right. Let me just get a bit of a start on the normal distribution, because we were running about 10 minutes. Or maybe I should wait for that for tomorrow. I'll pick up that tomorrow. Yeah, why don't we just go to Jose then? Okay. Do you want to take a 5-minute break or something, or do you want to go right to Jose?